Okay, hello class. We are doing sort of the second half of chapter 4 of journal 3. We're continuing on with volume, once again exact volume. Where we left off was we were really restricted in that we could only work on regions R that were rectangular. And now today we're going to look at other regions. Maybe we'll do, I think we're going to do a triangular one. Maybe we'll do one between a couple different functions, something that maybe looks like this. And then again, there's that's x, y. Z comes out from the board. There's some surface over this region or under it. You're always going to go from the surface to the region in the xy plane, and we'll get the volume of that exactly. So we're going to be able to go beyond these, where these were just clearly constant limits of integration on our double integral, to things where we'll have variables now in our limits of integration. But we'll still work it as an iterated integral, so much of the same stuff holds. It's just figuring out what are our limits of integration for things like this. That's really the tricky part. Okay, so I want to start with a couple examples. So we want to find the volume over R from y equals x to x equals y squared minus y under z equals 2x squared plus y squared. Okay, so they're just defining a region R in the xy plane, and it's, let's go ahead and graph this. Line y equals x, no problem. This next one is a function of f of y. And so I think it's going to be a parabola, but like turned on its side, because we see the parabola part. And so I think it's going to go like that, but let's figure out where. I'm just going to do a quick little xy table. And I'm going to fill in the y values, and then that'll give me the x's. So like when y is 0, x is 0. When y is 1, x is also 0. When y is 2, x is 2. Let's try like minus 1. Minus 1 squared. That'd be positive 2 again. Okay, so I got 4 points. Let's see if that's enough to give me the shape that I think it's going to look like. Or again, you can just put this on a calculator textual. So 0, 0, 0, 1. That'd be 1, 1, and this would be 2, 2, 2. Would be about like here. And then 2 minus 1 would be about like here. Okay, so I think I've got enough. These 4 points, and I'm just going to do something like this. Okay, so the straight line y equals x, and then x equals y squared minus y. So we really want the volume of the surface over that region. Well, what is the surface? Hopefully you recognize this. It is what kind of paraboloid? A circular or an elliptic? Hopefully you recognize right away. So it's like a squashed bowl coming up from the edge. So it's elliptic paraboloid that's coming, in this case, out from the board. And we want the volume from that surface to this region R. Again, it'd be a good idea to pause the video, go to CalcPlot3D, use the enter a region, enter this region, enter this surface, from there down to the xy plane to 0, and it'll show you with little prisms what that looks like. Well, we want to get not an approximate volume with Riemann prisms. We want to get the exact volume with the double integral. Okay, so we know exact volume comes from a double integral from the surface to the xy plane. So it's figuring out these limits of integration for this region. Now, it doesn't matter whether I say dy dx when I integrate this, or dx dy, right? They're both equally easy to do the integration, at least the first step of the integration. But one of these might be easier than the other when we're defining the region. So let's see how that goes. So if we started with y first, these would be y equals limits. As opposed to dx, the inside ones would be x equals limits. And so hopefully you can recognize this right away, that because this region is actually defined As I go, if I'm doing x equals, I'm starting left to right. If I'm doing y equals first, I go like this. So as I go from left to right, if I'm going to start with the x equals, as I go from left to right, I'm always going from this curve, the parabola, to this line. On the other hand, if I was trying to start with dy's, well, it's kind of confusing. On this part, I'm definitely always going from the line to the parabola. But what happens here, you have to split this into, from this surface, maybe right about here, from there to there, and then from there to there, you do something different. So that's why I say it's easier to look. It's not impossible to do it dy dx. It's just going to take more work because you're going to have to split this parabola, and you have to solve it for y. The reason I think it's easier dx dy, I saw that right away, is because one of these, well, actually, they're both easily solved for x equals, right? If I just flip this one around, x equals y. And that's going to make it much easier. So when I'm solving this with respect to x first, I always go from the parabola, y squared minus y, up to y. And then then the outer limits are y limits, and y goes from a constant value, and they're always constants, right? I need to have constants on the outside to evaluate this and get a number, because the volume is going to be a number. I don't want to give volume in terms of a variable. So I'm going to go from y equals 0 up to, this was the 0.22 here, so this is 0, 0, right? So I'm going from y of 0 to y of 2. All right, so now we just have to complete this integration. You can check your work with the check tool. I showed you how to do that with Wolfram Alpha's double integral calculator, and you can also check it with CalPlot3D's approximate volume with their Riemann calculator, and just making the number of rectangular prisms and bigger, and you'll get approximation that converges towards the exact value. But we're going to do exactly with integrals. So I need to integrate this with respect to x first. Remember, this is an iterated integral. I work from the inside out. And I haven't done anything to the outer integral, so I'm going to carry that along. And in this box here, then, I need to put the antiderivative with respect to x of 2x squared, which is going to be 2x cubed over 3 plus xy squared. I'm going to evaluate that. I've done the integration, so I'm going to evaluate it at the limits. At the upper limit, which is x equals y, minus what happens at the lower limit. And I'm just reminding myself again, there's several variables in here. Which one am I plugging in for? So I'm just reminding myself I'm plugging in the x's. These are x equals limits that go first. As you can do more of these, you might be able to just drop those as you go along, but I like putting them in there in the beginning, especially. All right, in this bracket then, I'm going to go ahead and plug in these things. What happens at the upper limit when x is y and I plug in y for x? So I'll have 2y cubed over 3 plus y cubed. Right, and then I'm going to, well, there's actually, I can simplify that. There's going to be what, 5/3 y cubes? Just add those together. That's what happened when I plug in at the upper limit. Now I'm going to do it at the lower limit. And I'm going to plug in, whenever I see an x, I'm now going to stick y squared minus y. So maybe I need some more space here. Okay, x equals y squared minus y becomes 2/3 times y squared minus y cubed plus y squared times y squared minus y. So that'll be y to the 4th minus y to the 3rd. All right, lots of stuff to clean up before we do this last little bit of integration, but it's not going to be a tough integration, I don't think. So maybe on this line. Five thirds y cubed. Let's just distribute some minus signs first. So this minus sign comes into here. So I'll have a minus y to the 4th plus a y cubed But I see those y cubes add up here, so I actually have 8 y cubes at this point. Then I'm leaving the messier part in the middle, minus this 2/3 y squared minus y cubed dy. All right, no problem integrating, no problem. It's this one I have to do some more work before I can do the integration. I think maybe the best way is actually to multiply that out, because you can't use the general power rule. You don't have the derivative of what's inside 2y minus 1 there. Can't put it in because it's got a variable. So I think let's just go ahead and take some time to cube that over here. So y squared minus y times y squared minus y times y squared minus y. Let's just take the first two here, or maybe we'll do the last two, leave that first one. Multiplying those, we'll get y to the fourth minus 2y cubed plus y squared. Now I'll have to FOIL this, distribute, 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 distribute. And we'll get y to the sixth minus 2y to the fifth plus 2y to the fourth minus y to the fifth plus 2y to the fourth minus y cubed. So we have some things that combine, y to the sixth minus 3y to the fifth plus 4y to the fourth minus y cubed. That's as good as we can simplify. We'll stick that in right here, all with the minus times 2/3. I forgot about that. So this goes here, y to the sixth minus 3y to the fifth plus 4y to the fourth minus y cubed, another parentheses, and dy. Again, not too bad to integrate those, but maybe let's do a little bit of combining of like terms. Let's see. Maybe let's go ahead and distribute this fraction, might make it a little bit easier. So that'll be minus 2/3 y to the sixth plus 2y to the fifth minus 8/3 y to the fourth plus 2/3 y cubed. All right, so we can combine some more like terms. I've got some cubes here, y cubed, so I've got 10/3 y cubed, and I got some y to the fourth, so that takes care of that and that. A couple y to the fourth here. That's 3/3. So that'd be minus 11/3 y to the fourth, and what's that? Minus, oh wait, so I just did the fourth, and then a minus, or plus 2y to the fifth, minus 2/3 y to the sixth. dy. Okay, so lots of algebra and arithmetic, and then we're finally ready to do some power rules and evaluate from 2 to 0. And let's go ahead and make some space and go ahead and finish this one. So, make some space. Okay, so we're going to need to integrate from 0 to 2, but now I'm going to go ahead and do the integration, put it from 0 to 2, one at a time. So that'll be y to the fourth over 4, so 10/4, which is 5/2, y to the fourth, y to the fifth over 5, so minus 11/15, y to the fifth, y to the sixth over 6, so that's plus 1/3, y to the sixth over y to the seventh over 7, so that's minus 2/21, y to the seventh. I like plugging in the lower limit, no problem. Upper limit, we'll get some fractions, a little bit tedious. So 2 to the 4th is what, 16? So we have 5 halves times 16 minus 11/15 times 32 plus 1/6 times 2 to the 6 is 64, is that right? And then minus 2 21s times 128 minus a big 0. Whatever that evaluates to is our exact volume. So peck away at a calculator with that. Do common denominators, however you want to finish that. That'll be our exact volume over this region. Okay, so that was our first one where we had a non-rectangular region, and we got to check which order of integration might be easier, and we decided that the integration with respect to x on the inside, so dx dy, made more sense in this instance. Now I want to do one more example. Of another non-rectangular region, a little simpler one. Different surface. Okay, let's look at this function sine y squared. And the region I want to look at is this triangular, little triangular wedge here. Okay, this surface over that region, well, let's think about this surface. We haven't done one like this, but we've done, say, like sine y. We know what z equals sine of y is. It's going to be that undulation thing, undulating sines that move like the x-axis, right? That's the free variable. And then the y squared, I think, is just instead of making it between -1 and 1, probably is going to change the range there, but it still have that same trig shape to it. And so we have this surface over this region. A little bit easier because it's not so nonlinear, it's this geometric region, but it's still not rectangular. And so once again, the volume getting exactly with a double integral, we can say dy dx, or we can say dx dy. Now, here's an instance where integrating one way might be easier than the other. So let's look at the first one. Sine y squared dy. If I'm starting to work from the inside out, can you do that? Well, by the chain rule, or however it was taught to you, you would, or the sine rule, sine of an angle, you need like a 2y in there, and there is no way you can put that in because it's got the variable in it. If you had a y here and just needed to put in a 2, you could do that. But that's not the case here. And you can go through all your tables of integrals, you won't see this. This is one that doesn't have a closed form antiderivative. On the other hand, though, if we can set it up as dx dy, this is no problem to do that first integral, and then usually as you're working your way out, things get easier, right? Because you're getting more and more constants in there, having less and less variables. So this would be the path we'd want to take, just like the last example, but for a different reason. The reason this time is because it makes the integration doable. And then we'll see what happens with our limits. So if I'm going to do this with respect to x, I'm going to need x equals limits here. So again, as x runs this way, it runs from left to right. So x goes from x equals 0, right? The y-axis is x equals 0, until it reaches y equals x, or x equals y. Right, so that covers exactly what we want. And then as we do the outer limits of integration, those have to be constants. Y goes from 0 to 1. Easy to see from the picture. So no problem setting up the integration this way. And now let's go ahead and do it. We work from the inside out. No problem. When x looks at this, this is all just a constant. So it just gets carried along and an x attached. So we'll have, when we integrate, sine y squared times x. And we're going to evaluate that at our limits, which are x goes from 0 to y. And then we'll eventually get to the outer integral dy. Okay, so I plug in my limits of integration at the upper limit. I'm going to get y sine y squared minus what happens at the lower limit, which is a 0, dy. So this is what I'm left with as a single integral. Now we're ready to say, okay, by the chain rule or u substitution or just sine of an angle, depending on how you learned it. This is everything we need except a 2. I'm allowed to put in a 2 because that's just a constant, as long as I take out its reciprocal. And in that way, you can see I haven't changed the problem. I've multiplied it by a special 1, 1/2 times 2. It's just a special version of 1, so I haven't changed the problem. But what I have done is I've like massaged it so that it fits the form of, you need the derivative of the angle, which is 2y in there. We now have it in there. And then you just integrate the antiderivative of sine is what? Is that minus cosine? Or yeah, I think it's minus cosine, right? Because the derivative of that would be, yeah, that's it. So minus, because if I take the derivative, I always forget my signs, but if I take the derivative of that, I do get a minus of a minus makes the positive. Okay, and then don't forget the 1/2 out front. So minus 1/2 cosine y squared. We've done the integration. Let's go ahead and evaluate then our limits. Upper limit first minus the lower limit. So minus 1/2 cosine of 1 minus plus 1/2 cosine of 0. Let's see, cosine of 0 is 1. So we'll have 1/2 minus 1/2 of cosine 1, whatever that is. Evaluate, you can get a decimal. And that is our exact volume. Let's see, and that would have to be a positive number, it looks like, because that's going to be a small number fraction. So it looks like it's going to be a positive number, which again means that this surface lies above the xy plane. But let's check all that, see if my intuition, my visual intuition on that is right. So let's see what the surface looks like, first of all, in Calc-Plot3D, and then we'll look at the region. Calc-Plot3D. Let's add the function, which was sine y squared. Yeah, okay, so we do have this, and maybe let's make it a little bit bigger just to see what is happening. And a few more grid lines to make it less blocky. Again, I can use my mouse, or it's really helpful if you just use your arrows and a little more control. And we were focusing though on this region from 0 to 1, so maybe let's just go back and focus. That triangular region is within this box. It's a triangle within this box. Okay, so there's our surface, and we do see that it is always above the xy plane, therefore we would expect to get a positive volume over a triangular region. So I'm going to then select to add a region to the graph, and the input is this purple area over here, and I want to make it look like our little triangular flag, I guess you might call it over there. So we went from the top would be y equals 1, and the bottom would be y equals x. X goes from 0 to 1. Let's see if that makes our flag. Yep. So it makes the flag there. And then the surface, though, that we want, we have a preset one. That's not what we want. We want to change that to sine y squared down to 0. Let's turn off the surface that we had. Put that one in, hit enter. Okay, so there is the surface to the xy plane. And again, here's the xy plane underneath, and you can see that is our flag. Let's maybe view it from above, and if you turn your head, there's the positive x, positive y, and it does make that flag. So there is our correct region, which is also shown in the left here, the purple region. But the surface now, coming back to our usual orientation, get that upright a little bit more. Z's pointing up, and we have this sort of section of a ramp almost to that triangular flag, and that volume we got an exact value down there. We didn't give us a decimal, but you could approximate it, make sure you show the Riemann prisms, and then ask you how many prisms. They're putting 16 prisms in here, 4 in each direction. Well, maybe they don't fill it all the way up because of the triangle, it looks like. Then there's 1, 2, 3. Some of them end up having a value of 0. And when you do that, and show the points for height, sometimes I don't know why it doesn't display the volume, but when you click this button, sometimes it does. So there's the estimate for the volume. It is an estimate, though, because it was doing it with the approximate volume with rectangular regions, where you're getting an exact value. You can see how good that estimate is if you turn ours into a decimal. And measure cycles again. Okay, so I think that's all I wanted to say with the TechTool share file. I'm make sure I did everything on that in the notes too. Okay, so I think that's it for volume over other regions. It's an extension of over the rectangular, and you'll have plenty of practice playing with switching from dx dy to dy dx. We'll also talk about that